Welcome to today's lesson. We are going to continue with applications of uniform circular motion, and today we have motion in a vertical circle. We are considering a ball of mass m that is tied at the end of a string, and it is moving with a uniform speed in a vertical circle of radius r. At any given time, the forces that are acting on this ball are 1. Its weight mg and tension of the string. This tension changes its magnitude depending on the position of the ball. For instance, we can have an object at point A. If you look at point A, we have that the mass, the mg, that is the weight of the ball, is acting towards the center, or it is acting downwards, and tension is also acting downward. So these two will give us the centripetal force. Remember, centripetal force always acts towards the center of the circular path. Therefore, we can have that our centripetal force mv squared over r is equals to Ta, that is our tension, plus mg. Then we can have a case where the ball is at C. If you look at this bottom part, you will find that the weight mg and the tension are in the different directions. So it means that to get centripetal force, which is our resultant force, it will be the subtraction of the two. So we shall have our equation like this, that our centripetal force is equals to Tc, that is the tension at C, minus mg. When we rearrange the two expressions or the two equations, we have the first one, we have that the tension at A, that is at the bottom, at the top, is equals to mv squared over r minus mg. Then the tension at C, it will be mv squared over r plus mg. If you look at these two equations, you will find that the tension at C is greater than the tension at A. Therefore, the tension in the string is at maximum in its lowest point. And at this particular point, you will find that the string may break. But the tension is minimum when the object is at the highest point. And at that particular point, you find that we must have a minimum speed so that we can keep that string taut. And for us to get that minimum velocity, then we say that the tension must be equals to 0. So we have this expression that mv squared over r minus mg, which is our weight, is equals to 0. From this, we have that mv squared over r is equals to mg. We have taken this mg on this side. And now we want to make this v the subject of the formula. So by multiplying by r over mg and getting the square root, you get that minimum velocity that is required for the string to be taut will be square root of rg. You can be able to see that that minimum speed or that minimum velocity depends on the radius because g is constant. We can look at practical examples of motion in vertical plane. 1, we have a pilot not stripped to his seat in a loop maneuver without falling. Then we have a bucket of water wheeled in a vertical without water spilling, or a ball bearing looping the loop on a rail line in a vertical plane. Then we have the motion in a horizontal circle. We want to look at an example here. Remember, when we have motion in a horizontal circle, the centripetal force is provided by the tension of this string. And the length of the string will give us the radius of the rotation. Therefore, this r will be the length of this spring. So we have the figure below shows an object at the end of a light spring balance connected to a peg using a string. The object is moving in a circular path on a smooth horizontal table with a constant speed. Now we move to the questions. 1. What provides the force that keeps the object moving in a circular path? That one, we have just mentioned that it is the tension on the spring. And that tension on the spring is providing the centripetal force. And the centripetal force, from the definition, is the force that maintains the body in a circular path. Then we are supposed to indicate with an arrow on the figure the direction of centripetal force. You know that centripetal force always acts towards the center of the circular path. Now, another question. The speed of the object is constant. Why is there acceleration? Now, when we consider the speed, we know that when we talk of speed, it is a scalar quantity. But in here, we are considering velocity. Because for us to have acceleration, we need velocity, change in velocity. The magnitude of velocity is not changing in this circular motion. But what is changing is the direction of velocity. At any instant, the direction of velocity keeps on changing, and that change in direction brings about the acceleration. So we have acceleration because the linear velocity changes in direction. Now, another question. Given that the mass of the object is 0.5 kilogram and it is moving at a speed of 8 meters per second at a radius of 2 meters, determine the reading of on the spring balance. Remember, the reading on the spring balance is now the value of centripetal force. Therefore, we can use the formula F is equals to mv squared over r. Then substituting the values here, we have 0.5 times 8 times 8 divided by 2. So that you get F is equals to 32 over 2, you get 16 Newton. So it means the reading on the spring balance will be 16 Newton, which is our centripetal force. Now, another part, we have that state what happens to the reading if the speed of rotation is reduced. This one is testing the factors that affect the centripetal force. We have talked about them. We have said the mass, the radius, and the angular velocity. So if you increase the angular velocity, the centripetal force also increases. And if you reduce, the force will also reduce. So it means if the force is reducing, the reading also decreases. We continue with another application where we have centrifuges. And this one is used for separating particles in suspensions, in liquids, or liquids of different densities. Now, it consists of small metal container tubes which can be rotated. These are the metal tubes that can be rotated. As you rotate, there is what we call the pressure difference that is created at a distance r. Our r will be the radius of the circular path. Remember, this one is rotating. So we have r, and this is where we have the liquids. So as you rotate, as you increase the rate of rotation, you will find that the force will increase. And as the force increases, you will find that the lighter particles, because this force will be too great for them, the lighter particles will come closer to the center of our circular path. That is, the less dense particles are drawn inwards towards the center of rotation, and the other particles will be towards the end. Then we look at satellites. We know that from Form 1, when we are talking about the types of forces, we have the gravitational force, where we said that it is the force of attraction between two bodies that are separated by any distance. So we have two bodies with masses m1 and m2 at a distance r from each other. They experience a force of attraction, and that force of attraction is given by F is equals to G m1 m2 over r squared, where G is universal gravitation constant and m1 and m2 is the masses. Then this expression is what we call Newton's law of universal gravitation, which implies if you have two bodies, Earth and satellite, the force of attraction between them gives us what we call the centripetal force. The formula for getting the centripetal force is mv squared over r. And we have seen that the force of attraction is G m1 m2 over r squared, where m1 is the mass of satellite and m2 is the mass of Earth, and v is the velocity of satellite. Remember, it is the one that is going around the Earth. And therefore, we can be able to get the velocity v of the satellite. If we combine the two expressions, we can make v squared the subject of the formula, where you have that v squared is equals to gm2. We have cancelled the m1 and we have cancelled one of the r. Therefore, we have v is equals to square root of gm2 over r. And from this part, we can say that our v is inversely proportional to the square root of our r, which implies that the velocity of satellite increases with the decrease in the radius. That is, the two are inversely proportional. If you increase this, it implies that the radius has increased. Or if you reduce the radius, then the velocity of satellite will increase. Sometimes, or at a particular point, you find that the periodic time of the satellite is equal to that of Earth. The periodic time, remember, the periodic time is the time taken to make one oscillation or one revolution. So because they are moving with the same time, then the satellite appears stationary when you view it from the Earth. And this one is said to be in parking orbit. And at that particular point, that is when it is used in weather forecasting or communication. Then we look at speed governors as another application. This one, it uses the principle of conical pendulum. Remember, we have said that in conical pendulum, as you increase the angular velocity, the angle increases. And also this one is also used in merry-go-round. So, as the angular velocity of the drive shaft increases, the mass is m1, m rises and moves the corer up as the angle theta increases. We have the arms are this one and the angle are this one. So as you increase the angular velocity of this, remember the direction of rotation is shown here. This angle will increase and the arm will rise, and they will make sure that the corer moves up. As the corer moves up, it moves the levers. You can see the direction of movement of levers at this particular point and this particular point. And these levers are connected to the fuel pump, or where we are getting the steam, or where we are getting the fuel. It is transmitted through a system of levers to the device that controls the fuel intake. And since the angular velocity of the drive shaft increases with the speed of the vehicle, that is, the angular velocity increases with the increase in vehicle, or in the speed of vehicle, then it implies that the fuel supply will cut off when the speed exceeds a certain limit. And that way you are able to control the speed of the vehicle using the speed governor. Thank you. Let us meet in our next lesson.